Yes, hello, Gretel. How are you today? This is Patrick Kamala, tutor educator, math and physics here, Roster Kulukwani. Yeah, today I want us to do the memorandum for May, June 2024. And as we discuss this, please try to understand, don't claim, because if you claim, you would not think right, okay? So, this video for two learners, those who are writing November 2024, which is on Monday, and those will be upgrading May, June 2025. Yes, understand. Let us start now. Yes, this is May, June 2024, as you can see it here, and we are starting right away with the question 1.1. The question says that the functional group for an aldehyde is, okay, so aldehydes, it's called a formyl group. Formyl group, that's aldehydes. Then the carboxyl is for carboxylic acids, carbonyl is for ketone, hydroxyl for alcohols. Let us continue. Which one of the following equation represents the reaction for the identification of unsaturated organic compound in the laboratory? Now, when we say unsaturated, we mean those which contain a double or a triple bond, okay, between their carbon atoms. Now, in this particular case, we add bromine to an alkene, and when we do so, we are going to get a bromoalkane, which has got two bromine atoms, okay? So, now it must be an alkene, all alkyne, okay? So if you check here, they're adding hydrogen, so that's not correct because we are adding bromine. Now here they're adding HBr, it's not correct because it must be bromine. Now here they're adding bromine, okay, and as you can see, this is an alkene here. What about here? They're also adding bromine, but here these are alkane. These are only single bonds. So if you take what they get here, they get bromoalkane plus H hydrogen bromide. So this is not correct because we must get a alkane with the two bromine atoms. Okay, so in this particular case, this is our answer whereby we add bromine plus an alkene to get this product here. So in this case, our answer is C. Okay. They say which one of the following is the empirical formula of ethyl ethanoate? Now, ethyl ethanoate looks like this. So it comes from this one here, okay, that is H3, then CH2, okay, then O here, and then ethanoate. We've got a carbon here with oxygen, then with this other CH, what? CH3, okay. So now, what is empirical formula? Empirical formula shows the simplest whole number ratio in which atoms are combined. Okay, so if you check here, how many carbons are here? This is 1, 2, 3, 4. So there are 4 carbons. Okay. What about hydrogens? 3 plus 2, that is 5. And 5 plus 3, that is 8. That means there are 8 hydrogen atoms here. If you look at oxygen, the oxygen, this is 1, 2. 2 oxygen atoms. So we're looking for the simplest whole number ratio. So we take out a common factor here. If we do so, we're going to have 2 into now, see what? C2, okay. Then H4, and then oxygen, just one atom, okay. So in this particular case, what you see inside here is called the empirical formula, which we call the simplest whole number ratio in which atoms combine in a molecule. So the answer is A. Hope we are together. Let us proceed. Next question here, 1.4. 1.4. 1.4, they say here that what must we do? 1.4, yes. They say here, in an experiment, 5 grams of calcium carbonate react with excess hydrochloric acid at a temperature of 4 degrees Celsius. This is calcium carbonate plus HCl to give us calcium chloride plus water plus carbon dioxide gas. They said that the volume of carbon dioxide gas produced versus time is shown by curve P in the graph below. The experiment is repeated with 10 grams of the same calcium carbonate sample and an excess of HCl with the same concentration of at 4 degrees Celsius. Which one of the curves now will be obtained? I repeat, in an experiment, 5 grams of calcium carbonate, okay, reacts with XAC hydrochloric acid at a temperature of 40 degrees Celsius. This is our equation here, okay. Then they said the volume of carbon dioxide gas produced versus time is shown by curve P in the graph below. So this curve P, which is solid here, okay. And then they said that the experiment is repeated with what? 10 grams of the same calcium carbonate sample at an excess of HCl with the same concentration of what at 4 degrees Celsius. So now in this case, the temperature is maintained, okay. The temperature is maintained here, but we have got more calcium carbonate. Here we have 10 grams. Here in this first experiment they had 5 grams, okay. Now from this particular case, now if you check what's happening here, because of the increase in the mass of calcium carbonate, we expect to get a higher yield of calcium carbonate. So if this is graph P, it means that we must have a high yield, which means that graph 2 and number 1, they are not correct because they give us the same yield and the lower yield, okay. And then if you check what we have now, because of the increase in the number of grams, it means that we are gonna have more calcium carbonate reacting, and thus we are increasing on the what? We are increasing on the reactancy, okay. So because of the more reactant, they're gonna be closer, and so they're gonna be closer in a given volume. And that particular case, what we see here as the graph 3, okay, we see it is of course higher than the one which is for what? Which is for 5 grams altogether. But then because of the more concentration of the calcium carbonate, you're going to take, it's going to be what? A steeper gradient than for curve P. So curve 3 is not right because it has got the same gradient as curve P, which was for 5. Now the 10 grams must have a higher gradient that makes it this curve number 4. So in that case, our answer is going to be what? It's going to be D. The answer there is D, okay. Hope we are together. Next question here, that is the question 1.5 now. 1.5 here, they said that the balanced equation below represent a reaction at equilibrium. This is chromate ions, which is yellow, okay, plus hydronium ions to give us dichromate, which are orange ions, plus water, which is liquid. They say which statements is or are true when a few drops of concentrated hydrochloric acid are added to the mixture. Okay, so remember that here we have the chromate ions, which are yellow, mean that if our solution contains chromate ions, it's going to appear yellow. And then we have the dichromate ions, which are orange, so mean that if you have got dichromate ions in the solution, it's going to appear orange, okay. Now what are we adding? We are adding a few drops of what? They say they add a few drops of concentrated HCl. Now this HCl, the HCl in solution, okay, it's going to give us if you put it in water, it's going to give us hydronium ions, okay, hydronium ions, and then chloride ions, okay, chloride ions. Okay, so these chloride ions which you see here, these chloride ions which you see, they're going to react with these available hydronium ions altogether, and as they do so, we're going to now form more of the product, okay, because from the Taylor principle, when we add a disturbance, it must be worked upon by reversing it, okay. So we're going to decrease the excess chloride ions by favoring what? The forward reaction. So when we favor the forward reaction, we're going to have more of the what? Of the dichromate ions, and hence we're going to have the orange solution as a result, okay. So for this matter, what we have, they're saying that the reverse reaction will be favored. That's not correct because already we have excess Okay, then they say here the concentration of dichromate ion is going to increase. Why is it increasing now? Because we are forming dichromate ions. Okay, that's why it's going to increase. And then said the color of the sodium solution changes from yellow to orange. Now, because of the dichromate ions present, you're going to have the orange color. So it must be 2 and 3. So for this matter, the answer is going to be D. Okay. Hope we are together. Let us proceed here. 1.6. They say that consider the equation below for a hypothetical reaction. Okay, means it's theoretical. That is A aqueous plus B solid to give us C aqueous plus D aqueous. They say if the equilibrium constant Kc is 1 exponent negative 4, then this is what happens. So don't forget that in our Kc expressions, we don't include solids. Solids must be out, okay, in our case expression, which means anything containing B is not correct. So it means not correct, so it's not correct here. We don't need to have B, so this must be out. Okay, now if you look at our Kc, for this particular equation is going to be given by Kc equals to C concentration, okay, multiplied by D concentration, okay, then divided by what? Divided by a concentration, okay. Now in this particular case, our case which we have is 1 exponent negative 4 means going to be 0, 0,0001. So because it is less than 1, it means what? In mathematics, actually it means we can say it's going to be 1 out of what? Out of 1, 0, 0, 0, 0. Okay, so in this particular case, it means that we are having a bigger denominator and a smaller numerator. So we're going to have a larger concentration of A, okay, which is going to be less than that of the product of C and D. So for that case, our answer is going to be C, because here we see that we have got a larger concentration of A and a smaller of C multiplied by D. So the answer there is C. Okay. Next question here. 1.7 is that which one of the following shows the products of the reaction of oxalic acid with sodium hydroxide? I repeat, which one of the following shows the products for the reaction of oxalic acid with sodium hydroxide? Now, oxalic acid with sodium hydroxide going to form sodium oxalate plus water. Now, all the oxalate ions, they look like this, okay? That is the C2, then O4 with the 2 minus. That's oxalate ions. So because we are adding sodium hydroxide, we're going to combine with the sodium ions, okay? Sodium ions, and this is positive here. So that's positive 1 here, okay? Now, in this particular case, if you check this one out here, if I can check what I have here, this is one positive sodium ion, right? And because of being 1, I needed 2 of the sodium ions to balance the what? The negative 2 on the oxalate ion. So in other words, my sodium oxalate is supposed to be C2O4, are we together? And then with what? With A, and then multiply by 2 here, okay? So because of what I can do here now, I can take out a 2. So I can write it as actually CO, then I put a 2 out here, okay? Then this sodium, 2 of them comes like it. So in this particular case, because I'm getting sodium oxalate plus water as my product, this must be the best answer here, okay? This is sodium ethanoate, so it's not correct. It must be sodium oxalate. Okay, hope we are together. Now here, it's correct, but because there's no carbonate, we can't get carbon dioxide, so it makes it to be wrong, okay? Then here, also wrong because there's no carbonate in our reactants, okay? But here, this is sodium ethanoate, but they talked about oxalic acid, so it must be sodium oxalate, okay? So the answer there is B. I hope, guys, we are together. Let us proceed. 1.8. 1.8, what does it talk about? Okay, 1.8 here, May, June 2024. They say here that the 4 solutions of different acids of the same concentration are compared. Which one of the following Ka values represent the weakest acid at 25 degrees Celsius? I repeat, 4 solutions of different acids of the same concentration, they are compared. Which one of the following Ka values represent the weakest acid at 25 degrees Celsius? Now, a weak acid, we know that it partially ionizes in a solution, okay? And so its Ka value must be very, very small. So we're going to check here which one has got the smallest Ka value. If you see what happens here, this is 4,5 exponent negative 6. It means what? It means 0, how many zeros? 1, 2, 3, 4, 5. Then you put the 4, it makes the sixth position there. That's what we have there. So yeah, what about here? This power negative 5, power negative 2. Okay, this one is going to be 0, 1, 0, it's going to be 0, how many zeros here? They're going to be 4, of course. This is 1, 2, 3, 4. Then what comes next is a 2 and then 5. What about here? It's going to be 0, 0, 1, 8. What about here? 0, 0, 6, and 5. So if you check here, because these are 4 zeros, it means I'm done with which is gonna be weakest here. It's gonna be which one here? How many zeros are here? 1, 2, 3, 4, 5. What about here? 1, 2, 3, 4. So this must be the weakest one because it's got the lowest Ka value, which shows us how the acid ionizes. So our answer is going to be A. Okay. Don't forget that the Ka shows us how much does the acid ionize in a solution. Okay, so that's the weakest one with the smallest value of the Ka. 1.9. Copper is purified by electrolysis. Which one of the following combinations is correct for the changes occurring at the anode, cathode, and in the electrolyte when the cell is in operation? I repeat, copper is purified by electrolysis, yes. They say which one of the following combinations is correct for the changes occurring at the anode, cathode, and in the electrolyte when the cell is in operation. So here we have the power source. This is anode, this is cathode. Now from our theory, when we are purifying copper, what we don't want, which is the unwanted copper, which is impure, must be put on the anode. Are we together? Why? Because at the anode, oxidation takes place there. Then the one which is pure but very small, we put on the cathode. Why? Because reduction takes place at the cathode. So, because oxidation happens at the anode, oxidation, it means you're going to destroy. You're going to break it into two small particles, okay? So in this particular case, as we destroy this anode here, it's going to decrease in mass. What about at the cathode? That's a reduction, which you can call build up or make up. We are adding a layer of copper. So the cathode is going to increase in mass, while the anode is going to decrease in mass, okay? But however, you're going to be having two reactions taking place simultaneously. That is to say, oxidation onto the anode and reduction this side. Because they do at the same rate, you're going to have the same concentration of the what? Of the copper ions in the solution. And so for that matter, our answer is going to be what? We say the anode is going to increase, it's going to decrease, okay? Because it is being eaten up, okay? It's going to decrease, okay? And then, while the cathode is going to increase, it's going to increase in mass, okay? And then, so, it has to be anode, decrease, cathode, it must increase. What about the electrolyte, the color of the electrolyte? Now, because we said, oxidation and reduction happen at the same time, it means that there must be no change. So the answer becomes B. Answer becomes B in this case. All right. Let us proceed here. They say here that which one of the following redox reactions is spontaneous under standard conditions? Which one of the following redox reaction is spontaneous under standard conditions? So in this, what we do here, we look at all the equations here, and as we do so, we are going to form a cell, okay, using table 4b. We're going to have the cathode and the anode out together, and after identifying the cathode and the anode, we're going to calculate our E for the cell for each of them, okay. That is E standard for the cell. Using what? We're going to use E standard for the cathode, okay, minus E standard for the anode, okay. Now in our table 4b, the one which is the anode, it's on above the other, okay. And so for that matter, when you do substitute and subtract for each of the cells, you're going to find out which pair is most positive. So the one which is most positive will give us the one which is most spontaneous. So if you do so for all of them, you're going to get B. Okay. If you don't get it, feel free to inbox me on 0785 222 Okay, that was question 1. So here we go to question 2, which is multiple choice. Yes, question 2, May, June 2024. The letters A to H in the table below represent 8 organic compounds A, B, C, D, E, F, G, and the H, okay? Define the term hydrocarbon. So what's a hydrocarbon, guys? Hydrocarbons, we know they are what? Hydrocarbons, they are organic compounds, okay? The organic compound that contain only what? Only carbon and not hydrogen atoms. So hydrocarbon, organic compounds, okay? Organic molecules, okay? That contain what? That contain only carbon and what? And hydrogen atoms, okay? Okay, next question here. They said that write down the letters for the following, okay? They said that 2 compounds that are unsaturated hydrocarbons, they must be unsaturated and must also be hydrocarbons. So what does the unsaturated hydrocarbons mean to us? Now, a hydrocarbon which is unsaturated, it contains single or triple bonds between its carbon atoms. So, I repeat, a hydrocarbon which is unsaturated, it contains double or triple bonds. So, in this particular case, the answer is going to be, it must be C and what? This is C and E. This one is a double bond here, then a triple bond for the butane, okay? Now we can talk about this H, because H, this double bond is between the oxygen and the carbon, but we talked about hydrocarbon, so it must be C and E. That's our answer there. It must be C and E. So here we have C and E. C and E. Okay, and then next here, 2 compounds that are chain isomers of each other. Chain isomers. And now, chain isomers, these are compounds which contain the same molecular formula but different chain. And being chain isomers, they must have the same position for the functional group, otherwise they're going to change, okay? So what could be the answer here? If you check what we have here, look at this compound D. Look at compound. How many carbons are here? This is 1, 2, 3, 4, 5. Okay. Now that is pentanal. 5 carbon atom aldehyde. What about down here? Let's check here. This is 1, 2, 3, 4, 5. So compound D and the compound H, they are what? They are chain isomers because they've got different types of chain. For example, here, the main chain has got 3 carbon atoms. What about here? They have 5 carbon atoms. So, and they have got the same molecular formula. So these are called chain isomers. So in this case, our answer is what? It is D and H. it is D and H. So there we have D and H. We have what? D and H. Hope we are together. Then it says secondary alcohol. Now a secondary alcohol should be one containing OH on the carbon atom that is bonded to two other carbon atoms. So in this particular case, butan 2-ol. Now but meaning 4 carbon atoms, can be 1, 2, 3, 4. So if you say butan 2 on carbon number 2, that is OH. So you see this OH is bonded to this carbon atom, okay? Is bonded to this carbon atom, this one here, okay? Which in turn is bonded to two other carbon atoms. So this and this one here. So it makes it to be what? To be a secondary alcohol. So the answer is what there? The answer is going to be A. The answer is A. The answer is A here. So that's our secondary alcohol. So the answer is A here. The answer here is A. Okay, then next here they said that write down the structural formula of the functional isomer of compound D. Now compound D, where is it? Is this aldehyde here? This is 1, 2, 3, 4, 5. That's pentanal. What must we do with it? Write down the structural formula of the functional isomer of compound D. Now, functional isomers, they are organic molecules with the same molecular formula, but different functional groups. And what we know from the theory that aldehydes, they are functional what? Isomers with the ketones. So, for that case, I'm going to get a ketone with the 5 carbon atoms, okay? All right, so for that matter, my answer is going to be like this one here. For 2.3.1, it's going to be like this. 2.3.1. Okay, remember there must be 5 carbons, né? There must be a ketone. That's 1, 2, 3, 4, and then 5. So I want a ketone, which means I can put my O here on this carbon atom, okay? All right, now each carbon must be having 5 bonds, né? Even if you're too much excited, don't put more than 5. You lose your marks, okay? So this is question okay, 2.3.1. This is 2.3.1. So we're going to put hydrogens now. Don't leave it pending. Please put the hydrogens. This is a ketone with the 5 carbon atoms. So it is a functional isomer with an aldehyde of 5 carbon atoms, which is called the pentanal. And I hope we are together. Okay. Next question. Let's check what I want here. That is 2.3.2. What must we do? They say write down the general formula of the homologous series to which compound B belongs. Now compound B, where are you? Now compound B, if you check here, this is CH3, C, then these are 2 branches on C. These are 2 CH2s, and so this is an this is what? This is an alkane. Okay. So being an alkane, how many carbons are here? This is 1, 2, 2 plus 2 makes it 4, 4 plus 4 makes it 4 plus 2 makes it 6, 6 plus 1 makes it 7. So I've got 7 carbon atoms, but what do we need to write down? Write down what? Write down the formula of the homologous series. Okay, so homologous series for the alkanes, we know it is CN, okay, CN, H2N, CN, H2N plus 2. Like for this case, what they gave us here, if you check it again, you see we said we have 7 carbon atoms, né? Let's check them out now, if it conforms to what we talked about here. It's going to be C7, okay. What 7 times 2? 14, plus 2, 16, okay. Now check here. These are 3 hydrogens. 3 times 2, that is 6. 6 plus 3, that is 9. Then 9 plus 4, it makes what? 9 plus 2 makes 13. 13 plus 3 makes 16, which means we are right. Okay. Next question here. Let's check it out. What must we do? Write down the structural formula of compound C. Compound C structural formula. Now, compound C is 3-ethyl pentyl-1-ine. 3-ethyl pentyl-1-ine. Okay, so for that matter, 3-ethyl pentyl-1-ine, this is how it looks like. 3-ethyl pentyl-1-ine. Now the pent means there are 5 carbon atoms, ne? This is 1, okay, 2, 3, 4, 5. So because they're saying pentyl-1-ine, if it's carbon number 1, you're gonna put a triple bond here, okay? Then they're saying 3-ethyl, ne? This is 1, 2, 3. Now put ethyl here, okay? Meaning 2 carbons, okay? And then that's all. Now you must put 4 bonds for each carbon atom. So this is 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 here as well. And then 4 here. So this is 1, 2, 3, 4. 1, 2, 3, 4. Now put the hydrogens. Okay. Put hydrogens, put hydrogens. Put hydrogens here too. Put hydrogens here. Put hydrogens here as well, and hydrogens here as well. Hope we are together. This is the structural formula for this compound. They said compound C. Okay. They said it is 3-ethyl pentyl-1-ine. Must be hydrogen here. Okay, next question here. What must we do? Yes, now they say IUPAC name of the compound E, G, and H. Compound E, IUPAC name for compound E. Now, compound E, if we can say this is 1, 2, 3, 4, 5, we're not right because we are leaving out the functional group. So we rather say 1, 2, 3, 4, 5, 6. Okay. So this is our longest carbon chain. The longest continuous carbon chain. Longest continuous carbon chain. Okay. So in this particular case, on our chain, on carbon number 3, we have what? We have a branch which is ethyl. Okay. So what could be the name now? You're gonna say 3-ethyl. We say what? You're gonna say 3-ethyl. Okay. And put it here. I'm gonna say 3-ethyl. Okay. 3-ethyl. Because there are 6 in the longest chain, I'm gonna say hex. Now, where is my double bond on carbon number 1? On carbon number 3 is going to be X3, okay? X3. Now, being an alkene, it must end with ENE, Hex3ene, which is 3-ethyl Hex3ene. It is 3-ethyl Hex3ene, okay? Then they say the E and the what? The E and G, okay? Now our G is this one here. If we can say this is 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Okay, now the chloro come first in the alphabet, né? So it's gonna be 2 chloro. This is 1, 2, 3, 4, 5, 2 and 5, okay? 2 and 5, right? This is carbon number 1 here. 2 and 5. 2 and so this is carbon number 1, okay? And then carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, okay? So on carbon number 2 and carbon number 5, we have what? The chloros. So I'm going to say 2,5 dichloro, 2,5 dichloro, okay, dichloro. And then what about the methyls? 2, 4 dimethyl, 2, 4 dimethyl, okay. And then the longest chain, there are 6, will be now hexane because they are single bonds, okay. Okay, this is 1, 2, and dimethylhexane, dimethylhexane. So that's the answer here. It is 2,5 dichloro, 2,4 dimethylhexane. Next, we say the G and is it and the H? Let's check it again. And the H as well. Now with our H here, now this one is an aldehyde, so that's 1, 2, 3 with 3 carbon atoms. Now these are the branches. It's a branch here and a branch here, and carbon number 2. So we're gonna say 2,2. We say what? 2, 2 dimethyl, 2,2 dimethyl, 2,2 dimethyl propanol. Dimethyl what? Propanol, because they're only 3 carbon atoms, ne? Propanol. Okay, let us continue then. Next question here. There's a compound B undergoes complete combustion. Using molecular formula, write down the balanced equation for this reaction. Now our compound B was compound B is this alkane here with 7 carbon atoms, ne? So let us balance it here. Compound B undergoes complete combustion. So being 7 carbon, you're gonna say it is C7 here. C7. What 7 times 2 again? 14 plus 2, 16, okay? Then plus oxygen here to give us carbon dioxide, okay? Carbon dioxide, then plus water or plus steam. Now to balance this one here, if you check there are 7 carbons here, we can put a 7 here to get 7 carbons. What about hydrogens? There are 16 here, so we can put 8 here because 8 times 2 is 16. What about oxygens now? Now 7 times 2, it makes 14. Then 14 plus 8, it makes 22. So to make 22, I just put 11 here because 11 times 2 is going to be 22. So it's now balanced. Okay, so hope we are still together. May, June 2024. Question 3. They said that the boiling points of some organic compounds are shown in the table below. The atmospheric pressure is 101,3 kilopascals. Organic compound boiling point at A, B, C, and D here. Then the boiling points you have 7, 8, 4, 6, 1, 1, 8, and X here. Define the term boiling point. Define the term boiling point. So what is boiling point? Question 3.1. What is boiling point? What is boiling point? Talk to me now. Now boiling point is the temperature. Okay. Boiling point is what? Boiling point is the temperature. The temperature at which the vapor pressure of a substance, okay, vapor pressure of a substance is equal to the atmospheric pressure. atmospheric pressure. Okay, next question. They said that I must do what? Let's check it out. After defining boiling point, what must we do next? Which one of the compounds A, B, or C is mainly in the liquid phase at 100 degrees Celsius? So now the first one, A, it boils at 78, which means at 80 it's no longer a liquid, but now it's a gas. Because 78 started boiling, so it's now gas and liquid. What about here now? This B, 46, it is boiling, so it means 50 already there is some gas. Okay, so by the time we reach 100, almost the gas is finished completely. So they said is liquid mainly. Okay, look at C. Now C, when you reach 90, it is still a liquid. Reach 100, still a liquid. 110, still a liquid. 115, liquid. So the answer must be C because it boils above 100. So the answer is what? The answer is C. The answer here is C. Okay. Explain the difference in the boiling points of compounds A and B. Now, compounds A and B, okay, A and B. If you look at compound A, it is linear. Compound B, it is branched. There's a branch here, okay. So, being linear in A, you're going to have larger surface area for intermolecular forces to act out together. So, you're going to have stronger intermolecular forces in A as compared to B, and hence more energy to overcome these forces in A compared to B, and hence a higher boiling point in A than B. So here we go. There's a difference in boiling points between compounds A and B. We're saying that A has got what? It is longer, okay, than B because B is more branched. So because of that, it has got a larger surface area for the intermolecular forces to act, that's London forces, okay. While in B, it has got less surface area. So because of we're going to have stronger intermolecular forces in A molecules than what? Than B molecules. So more energy required to overcome these big forces in A than in B, and hence a higher boiling point. Okay, next here they say that consider the following points below, boiling points below: 75, 120, 126. Which one of these values represents X, the boiling point of compound D? Now, compound D, if you check it here, compound D is an aldehyde because this is CHO, aldehyde. Then compound, they said compound A, okay. So this is 75, and if you check what we have, this is 78. Now, 78 is a alkane, okay. Now, alkanes have got stronger dipole forces more than aldehydes, okay. So because of that, let's check it here. They say that which one of these values represents X, the boiling point of compound D? So because of that, means that our answer here must be 75. It must be 75 here because the aldehydes, okay, they've got weaker forces as compared to what? To the dipole forces in what? In alkanes, in alkanes. So the answer is what here? It is 75. Okay, then here let's say explain your answer to question 3.4.1. Now 3.4.1, if you check what you have here, now this one is also 1, 2, 3, 4, okay, but being an alcohol, it has got stronger boiling hydrogen bonds than D. That's why it can't be around this one here. Then if you look at this one here, which is branched, now this one B, which is branched, has got a very low surface area, so it must be less than what? Less than X. Okay, let us proceed. They said the atmospheric pressure is now changed to 83 kilopascals. How will the boiling points of these organic compounds be affected? Choose from increase, decrease, or remain the same. Now, this particular case, our atmospheric pressure is 83 kilopascals, as compared to the first one, which was how much? They say it was 101, 3 kilopascals. So, because of decrease in atmospheric pressure, it means that our boiling points, in this case, they must do what? They must decrease. So they decrease. They do decrease here. Okay, next question here. Question 4, May, June 2024. In an experiment, a test tube containing methanol, propanoic acid, and catalyst is heated in a water bath. Water bath is here. Methanol, propanoic acid plus catalyst. This is the heat here. Write down the name or formula of the catalyst used. So because we have methanol and the propanoic acid, we know this is esterification, where we use what? Sulfuric acid, which is concentrated. So we're going to say here it is what? It is concentrated sulfuric acid. It is concentrated what? Sulfuric acid. That's our answer here. Then the setup of reaction taking place, we say it's called what? It's called esterification. It is called esterification. It is called what? Esterification. Esterification here. And then next, question 4.1.3. They select down 2 reasons why the use of a water bath is preferred in this experiment. Now, why do you need a water bath? Because methanol is flammable. Because what? Methanol is flammable. So we need a water bath because methanol is flammable. So it might catch fire. Okay. So apart from this, what this one here, the water bath helps us to heat the contents evenly. So for even heating, okay, for evenly heating the test tube contents, so that we can evenly heat the test tube contents. Test tube contents. Okay. Okay. Then next question here, they said that 4.1.4. The balanced equation for this reaction is using structural formulae. Now, this reaction is called esterification, where we are reacting methanol plus propanoic acid to give us what? To give us methyl propanoate plus water. Okay, so this is how it goes: methanol plus propanoic acid. Okay, so here we have the methanol, that is 1. Okay, methanol plus propanoic acid. This is methanol here. Methanol plus propanoic acid. Now propanoic acid has got 3 carbon atom. This is H here, 1 O, 1 carbon here, like this. Okay, carbon here. Okay, then we must put the other hydrogens. Each carbon must be having 4 hydrogens, né? So maybe hydrogen here, the hydrogen here, the hydrogen here, and the hydrogen here as well. Now when we heat this one here using the sulfuric acid, which is concentrated, so we do sulfuric acid and then heat. Okay, this must be concentrated. Okay, we're going to get methyl propanoate. We're going to get what? Methyl propanoate. Now the first carbon from methanol forms the methyl. Okay, like this. So this O came from the alcohol. Then now bringing this carbon here with its own O, this other carbon, this one here, then put H here. Okay, so like we said, each carbon must be having 4 bonds, 4 bonds, 4 bonds, 4 bonds. Okay, yeah, then plus water. That's plus H2O plus water. All right, that's what they wanted there. Let us continue here. They said that IUPAC name of the organic product formed for this reaction. So IUPAC name for this one here, begin with the first part of the alcohol, which is the methyl. Yeah, forgot to put hydrogens here. This one here must be having 4 hydrogens as well. Now this first part, it forms the first part of the name. Let me use red here. Let me use red. Now this first part of the compound, this one here, it forms what we call as the methyl. Then the last part here, which I'm putting now in green, this one here, it forms propanoate. Okay, so the name is going to become what? It's going to become methyl propanoate. Methyl propanoate. Methyl propanoate. Methyl propanoate. That is it there. Hope we are together. Let us proceed. Question 4. Yes, once again, this is question 4.2, May, June 2024. Okay, question 4.2. Compound A is a 6-carbon branched haloalkane. It's a branched haloalkane, okay. It is used in a 2-step reaction to prepare compound C. They say that reaction 2 is an addition reaction. So this is compound A, the haloalkane, and the reaction 1, reaction 2. But they give us a clue. They say that in this case, they say that our reaction 2 is what? They say reaction 2 is addition reaction. Now, if you look at what we have from the haloalkane to this alkane, okay, this one gives us a clue of what our haloalkane might have been. Now, the second reaction 2 is what? It is addition. So, what do we do? And they say, write down the name or formula of the inorganic reactant in reaction 2. Now, because we are getting an alkane and it is addition reaction, we can only add hydrogen to an alkene. So it means in this particular case, our answer 4.2.1 must be adding hydrogen. Okay, so that's hydrogen here. That's our inorganic reactant. Then IUPAC name of compound B. Now, if you check what we have here, because of this alkane here, means that our haloalkane must have been something like this, okay? This carbon here, this carbon here, this carbon here, this carbon here. Depending on the alkane, okay? It means that the alkane must have had some halogen somewhere here. Okay, we can put it here. We can put a bromo here. Okay, on this carbon here. But they want here compound B. Now this compound B must be an alkene. So an alkene, we want IUPAC name. So from here, we see that we can get our clue from something like this. Okay, this one here, this one here. Remember these branches here, we have them here as well. Okay, this is a methyl, and also here we have a methyl branch. Okay, and then a methyl branch here as well. Now the double bond cannot be put anywhere around this carbon, because if we do so, it's going to be having 5 carbon atoms. I repeat, remember that this is an alkene, which I'm adding to. Okay, must be an alkene, because I'm getting what? I'm getting alkane in here. Okay, this is alkane here. So now this alkene I'm talking about, this one here, I can't put double bond here, because this carbon will be having 5, which is not allowed. So my double bond must be here, and hence I'm going to get my name for compound B. So I'm going to fill this carbon number 1, carbon number 2, carbon number 3, and the carbon number 4. So on number 3 there are 2 methyls, so the name will be what? Will be 3 comma 3 3 comma 3 dimethyl, okay, dimethyl, and then what? Because there are 4 carbons, I'm going to say bute, dimethyl bute, okay, dimethyl bute. Now the double bond is on carbon number 1, so I'm going to say dimethyl bute 1 in, dimethyl bute 1 in. That's the name there, dimethyl bute 1 in. Next question here. They say now that the type of reaction by reaction 1. Now reaction 1, if you check here, because I was having a halogen in my alkane, but now it's not here anymore. I have removed the halogen together with one of the hydrogens which was here, okay? So I am eliminating HBr, so I can say dehydrohalogenation, or I can say that is elimination, okay? So reaction 1 must have been what? Elimination reaction. Must be elimination reaction, or I can call it what? Dehydrohalogenation, okay? So I am eliminating HBr, okay? Then there's a compound B is now used in two-step reaction to prepare compound A. So this compound B which you see here, let us draw it again for our clarity. Okay, if you draw it here again, compound B, you're going to have it on here. This is CH3 here, even here CH3. Then this one here, it is our CH, okay, CH. And then we have a double bond here, which is CH2, okay. All right, that's compound B. So then from here now, they said that compound B is now used in two-step reaction to prepare compound A, which compound A is the alkane, okay. Now they said that also reaction 4 is what? It is a substitution reaction. Okay, so this reaction is 3, then 4 here, and then compound A, don't forget it is a alkane, which we said like this one here, okay, most likely like this one here, okay. So this is H3, this is H3 here, okay. This is CH, okay, CH here, then CH3 here. So this must have been our compound A, approximately. So what must we do? That in this case, reaction 4 is substitution. Reaction 4 is what? Substitution reaction. And then they say what must we do? Let's check it here. Write down the name or formula of the catalyst used in reaction 3. Now from the alkene, then they're saying reaction 3, compound B, and they say reaction 4 is substitution. So because this is alkene, it means where there is bromo here, there must have been something for compound D, which is being substituted for in reaction 4. I repeat, because my compound A is this one here, probably, okay, it means that where there is bromo here in compound D, there must have been something. So because this is an alkene, I can use water in place of sulfuric acid as my catalyst. So if for that case, I'm gonna say here, if I use from this reaction, if I use what? Yes, if I'm gonna use if I'm gonna add water, which is H2O, to create my banal alcohol, then I'm going to use what? The acid here. So my catalyst here is going to be sulfuric acid concentrated, okay? It's going to be what? Sulfuric acid concentrated. It's going to be sulfuric acid concentrated, okay? That is it there. Then they say hypercarbonic compound D. Now compound D is the same as this one, only that maybe it's going to be having OH. Okay, so look like this, okay? Like this one here, I'm gonna have the metals here, another metal down here, okay, then CH here, but then I'm gonna have OH here because I'm adding water, okay. Then I'm gonna have my what? My CH3 here. Okay, so in this case, I'm to name this now. I'm gonna say it's carbon number 1, 2, 3, 4. So now I want a compound. We say I've got this methyl here, okay, another methyl here, okay. So I'm gonna say 3, 3 dimethyl. I say what? 3, 3 dimethyl, okay. Now because it's an alcohol, I'm gonna say butane, okay, butane, 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 B-U-T-A. Now my original carbon number 2, butane 2 all, butane 2 all. Then they say type of reaction by reaction 3. Now type of reaction here, because I am adding water, I'm gonna say addition. So this is addition reaction here. This is addition reaction. Addition reaction. Addition reaction. Okay, then they say here the type of alkane then by compound H is from primary, secondary, tertiary. Now, like you saw it here, our alkane, because the bromo is bonded to this carbon atom. Okay, there's a red color here. The bromo, this bromo which is the halogen, bonded to this carbon atom here, which carbon atom in turn is bonded to two other carbon atoms. Let me put them in the green. This one here, okay, and this one here. Because they are two, it becomes what? It becomes a secondary alkane. It becomes what? It becomes a secondary alkane. Hope we are together. Hope we are together. Yes, question 5, May, June 2024. The reaction between aluminium and excess sulfuric acid is used to investigate factors affecting rates of reactions. I repeat, the reaction between aluminium and excess sulfuric acid is used to investigate the factors affecting rates of reactions. Okay, so it's aluminium plus sulfuric acid to give us aluminium sulfate plus hydrogen gas. Okay, investigation 1, the effect of the catalyst. So here we are investigating the effect of the catalyst on the rate of the what? Rate of the reaction. Let's find out. They say that here, aluminium powder of mass 5 grams reacts with excess 0.1 mole sulfuric acid at 60 degrees Celsius. Then they say that consider the following energy diagrams not drawn to scale for this investigation. X and Y in diagram B represent activation energies. Okay. Alright, so this is diagram A and this diagram B here. What are we supposed to do here? They say that is the reaction between aluminum and sulfuric acid exothermic or endothermic? Give reason for your answer. Now, if you look at our energy here, for the products it is 86.5, but about reactants is 208.2. So because energy for the products is lower than that of the reactant, means it is exothermic. So here we say this is exothermic. We say this is what? This is exothermic. So this is exothermic. Give reason for your answer, because energy for the products, okay, energy for the products, okay, is what? Is lower than energy for the reactants, lower than energy for the reactants. Okay, then next question here says that let's say, what does the shaded area to the right of line P represent? Now this is the number of particles. Now this area here, if I may call it area 1, okay. Now the question talks about area 2, this area 2 here. Now area 2 shows those particles which have got sufficient energy for effective collision. So it shows the number of particles, okay, the number of particles, okay, with what? With sufficient energy with sufficient kinetic energy for effective collisions. Okay, that's for area 2, for effective what collisions. Then if we talk about area 1, now these are the particles which don't have enough energy. Okay, now here they say next that we must do what? Check it out. Determine the numerical value by letter XC on diagram B. So this letter X on diagram B, if you check our diagram A, that letter XC shows, because you see it has got a higher energy than Y, okay, it means that it must be correspond this value here, this 240,8, okay, but because we want the numerical value, they said X and Y, their activation energies, remember they said it here. Now being activation energy, we count it from the reactance, okay, so it's going to be from this point here up to here, okay, so this is our X, this is our X here. Now to get this X, what do? We subtract the height, that's 240. We say 240, 240,8, 240,8, then minus what? Minus 208,2, minus 208,2, and what do we get? It gives us what? Calculators, 240,8 minus 208,2. 240,8 minus 208,2. Here it gives me 32,6 kilojoules. So this is 32,6 kilojoules. This is 32,6. Here I get 32,6. 32,6 kilojoules. That's kJ. Next question here. What must we do now? They said that we should do what? Okay. Now investigation 2. The investigation is now repeated at 30 degrees using the same reactants. That's 5 grams aluminum powder and excess of common moles of sulfuric acid and the catalyst. Okay, they say how will this affect each of the following when compared to investigation 1? Choose from increases, decrease, or remain the same. So here the difference here is that if you check what's happening here, they're repeating it at 30 degrees Celsius. But look at our investigation 1. What was the temperature? Investigation 1. The temperature in investigation 1 was it was 60 degrees here. Okay, so now it means we are dealing it with at a lower temperature. So what do we expect? They're saying how would affect what now? Let's check. They said that the investigation is now repeated at 30 degrees Celsius using the same reactant C, okay, and the catalyst. They say how will this affect each of the following when compared to investigation 1? Choose from increases, decreases, or remain the same. So the size of the shaded area. So because of the lower temperature, we won't have many particles with effective collision in it. So that our shaded area must gonna decrease. Okay, it decreases. Now that which is shaded, that's what I call the area 2. Here we said it decreases. Okay. Then the value of y. Now the value of y, if we check it again here, y is the activation energy, like they told us here. This activation energy is here. So that one will not change. It will not change because it is independent of the temperature. So we say remains the same. So remains the same. Okay, remains the same. Then they say the total volume of hydrogen gas produced. Okay, now the total volume is going to be the same, but will be collected at a lower rate. So we say also remains the same. Okay, so that's what remains the same because it depends on the reactants which we are using in this case. Okay, not on the temperature. Okay, they say here that investigation 3. In this investigation, 5 grams of the same sample of the impure aluminum powder reacts with an excess sulfuric acid at 60 degrees Celsius In each of three lanes, the table below summarizes the conditions and the results obtained. Okay, I repeat. In this investigation 3, 5 grams of the same sample of impure aluminum powder react with what? With the XAC, that would sulfuric acid at 60 degrees, like in experiment 1. In each of the 3 runs, they said that the table below summarizes the conditions and results obtained. Assume that impurities do not react. Okay, all right. Let's check it out now. This is run 1, 2, and 3. What are they changing here? This is 0, 0,1, 0, 2, 0,4. This is the rate of the production of hydrogen gas. This is 15, 19, and 40. Let's write down the independent variable for this investigation. Now let's listen carefully here, learners. Now the independent variable is defined as that variable which the experimenter changes. So these learners, what are they changing? It's going to be our independent variable. So if you check here, they keep on changing the concentration because at first it's 0, 0,1, 0, 0,2. So the answer here is going to be what? It's going to be concentration of sulfuric acid. It's going to be what? Sulfuric acid concentration. This is our independent variable because they keep on changing it. Okay, next question here. Use the collision theory to explain how the average rate of the reaction is affected in this investigation. Now, if you check what happens here, guys, at 0, 0,1, the rate is 15, 0, 0,2, rate is 19, 0, 0,4, rate is 40. So, what do we notice? What do we notice? We notice an increase, right? Right? We said when we have increase in concentration, what happens? We see that the rate also increases. Ne? The rate does what? Increases. So they say that explain using what? The collision theory. So first of all, increase in what? We're going to have increase in what? In the sulfuric acid molecules. Okay, that is question 5.3.2. What do we say here? We are going to say that we explain like this. That's 5.3.2. There is what? There is increase. Okay, there is increase in the what? In the particles of what? Of sulfuric acid concentration. Okay, increase in the what? In increase in sulfuric acid particles because of the increased concentration. Okay, so if these particles increase, what do we expect then? Then we expect it leads to what? This leads to increase the effective collision. Okay, increase the effective collision. Okay, now don't forget that these particles, they're increasing per unit volume. Ne? Per what? Per unit volume. Per unit volume. Okay, now which lead to what? To increase the collisions that are effective, to increase the effective collisions. Ne? Now because these are effective collisions, what do we get in return? We're going to get what? We're going to get an increase in the reaction rate. Okay, we get what? Increase in reaction rate. Increase in the reaction rate. Okay. Next question here. What must we talk about? They say here that that the time for the reaction to reach completion in run 3 is 2.6 minutes. Calculate the percentage purity of the aluminium. Take the molar gas volume as what? As 60 to be 2700 cubic meters per mole. Okay, so now in this case, they gave us the time taken, okay, and then they're saying run 3. So because of run 3, it means what? It means that we are going to use that 40, okay, we're going to use this 40 here in our calculations, okay. So what do we know? Let's check it out again. Now here we have the rate, which is 40. Then we have the concentration, which is 0.4. All right, now this rate is for the hydrogen gas, okay? So because we have the rate, we can use it to find the volume of hydrogen gas. Then we're going to use the molar volume to get the number of moles. Then you compare with aluminium, and then you're going to get our mass of the pure aluminium, because that's what reacted. I repeat, I'm going to do like this. I'm going to use the rate, which is 40, okay, to find the volume of hydrogen gas. Then the volume of hydrogen gas, I'm going to find number of moles. Then from there, I'm going to use the mole ratio to find moles of aluminium that is pure, which reacted, and hence the mass, and then get my what? My percentage purity. So here we go. So they gave us 40, but what do we know? Now, depending on the units for the rate, which is the cubic centimeters per second, I'm gonna say that my rate, okay, the rate, that is 5.3.3, okay, the rate equals to what? Look at my units. They said here must be now change in volume, okay, change in volume divided by what? By change in time. Okay, so because the rate is 40, I'm gonna say this is 40. Now this is for hydrogen. Eh? Now the change in the volume here of hydrogen is what we're talking about here. Okay, so okay, change in volume of hydrogen, and then if it takes how much time? It takes how many minutes? Okay, let's check it here. They said that it takes 2.6 minutes. Okay, so divided by 2.6, but because this is per second, I must convert from minutes to seconds. Okay, I'm gonna say 2.6 here multiplied by what? By 60. So I can put them 2 seconds. So it means my change in the volume, or my volume of hydrogen gas that was used in that case, okay, in that run, gonna be divided by 40 multiplied by 2.6, okay, then times 60. So what do you get calculators there? With my calc here, I'm getting 2640 cubic centimeters. This is 6240. I'm getting 6240. Now these are centimeters cubed, okay? Now because I have the volume of hydrogen, okay, then I can now find the number of moles of hydrogen using this molar volume given to me here, okay? We know that number of moles equals to what? Equals to volume divided by the free molar, okay? So in this case, the volume which I got is 6240 divided by what? By 27300, by 2700. Okay, so I get which number of moles here. Calculators, what do you get there? So here with my calculator, I'm getting 0.2311 moles. 0.0, getting 0.2311 moles of hydrogen. Okay, now if I look at my mole ratio and I compare hydrogen to aluminium, because the question is about aluminium here, this is 2 moles to give 3 moles, né? So the mole ratio is 2 to 3 for aluminium and hydrogen. So let me check it out now. So if I do like this now, if I say 2 aluminium, okay, moles produce 3 moles of hydrogen, okay. So now the mole ratio is what? It is 2 is to what? Is to 3. But now I have the moles of hydrogen here. I'm going to put them here and I say 0.2311. Now here I'm going to put x here. Then you know we cross multiply, okay. So x times 3 gives us 3x, okay, equals to 2 times 0.2311, okay. So divided by 3, which gives us x equals to what? Which gives us 2 times 0, 2311 divided by 3, which gives us 0,154. 0,154. Now these are the moles of aluminium which reacted. Now since we have the moles of aluminium which reacted, you can find the pure mass of aluminium which reacted. Okay, what do we use as our formula, guys? You know that number of moles, okay, moles equals to mass divided by molar mass. So therefore the mass of the pure aluminium which reacted is gonna be moles times molar mass. Okay, so the moles here we have 0,154. 0,154. What about our molar mass for aluminium? What is it? From the periodic table there, it is 27. Okay, so times 27. That's what do I get here? Calculator here, I get the mass of the pure. This is 4,16. It is 4,16. 4,16. Okay, maybe at first they used 5 for the impure. So to get now my percentage purity, I use mass of the pure. Okay, mass of the pure divided by mass of the impure. Okay, mass of the impure then times 100. Okay, times what? Times 100. So let us now substitute. So we're going to have 4,16 divided by 5 times 1 times 100. So calculate what you get there. On my calc here, I'm getting 83.2%. So this is 83.2%. I hope we are together. Let us proceed then. Yes, now this is question 6, May, June 2024. Question 6, May, June 2024. Consider the balanced equation for the hypothetical reaction that takes place in a 2-decimal cubic container. So this is our reaction, which is P2Q plus 3Q solid to give us 2PQ2, guys. Okay, the graphs below, not drawn to scale, are obtained for the same reaction at 2 different temperatures. It is the same reaction. Did you see that? It's the same reaction at 2 different temperatures. So check what happens here. Now if you look at our the graph A is obtained at 298 Kelvin. What about graph B? 398. So graph A is at 298 Kelvin, then graph B is 398 Kelvin. Okay, so difference is 100. So this graph A here. Now note that what we have on the y-axis, this is the concentration in moles per decimeter cubed. What about here? Time in minutes. What about here again? Graph B, we have concentration in what? Moles per decimeter cubed. Also time here. Now note something that this PQ2 is our product. PQ2 is our what? Is our product. Okay. What about the P2Q? Now this P2Q is our reactant. Okay, is our reactant. Look at our diagram here, guys. Now from the beginning, the P2Q, which is the reactant, is above 0,4 moles per decimeter cubed. You can see that from somewhere here, how together. Then it decreases until the curve becomes flat. Then from the start, this one is 0. This is 0 from the start of the product, which means initially in our container, we are starting with what? We are starting with only P2Q, and we don't have any of the product. Okay, so it's going to increase, and then it becomes flat. Okay. Now graph B, after increasing the temperature, check what happens now. They're saying this is our reactant again. This must be the product, okay, which begins from 0. Now in here, if you look at our product, They called it P2Q. They call it what? P2Q instead of PQQ. So agree with me, this is not right. Okay, it was a typing error. This must be what? Must be PQ2 because this is just a change in temperature. It cannot change it cannot reverse the graphs like this. Okay, so this one here now it's supposed to be what? P2Q. So this is P2Q. What that is our reactant, né? It shows that it's going to be what? P. It is P2Q. Okay. What must we do now? They said that from there, this is a lower temperature than this one here. Say, state what? Le principle. How do we state it? How do we state Le principle? Anybody who remembers? That is 6.1. What do we say? 6.1. How do we state it? We said that when, okay, we said that when equilibrium, okay, when equilibrium of a reversible reaction okay, of a reversible reaction where in a closed system is disturbed, okay, what does the system do? The system will reinstate, okay, the system will reinstate, okay, reinstate a new equilibrium, okay, a new equilibrium by doing what? Equilibrium, okay, by doing what? By favoring the reaction, that opposes the disturbance, opposes the what? The disturbance. That opposes what? Opposes the disturbance. Okay, I repeat. When equilibrium of a reversible reaction in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. Okay, let us continue then. What must we do here? They said that what do the parallel lines after t equals to 5 minutes in the graph A represent? Okay, what do they represent? So after t equals to 5 minutes, what do we see here? That the lines become horizontal, they become flat. Now in here we say we have attained what? Chemical equilibrium. Okay, so 6.2 we have attained what? Chemical equilibrium. That is 6.2. We have attained chemical equilibrium. We have attained chemical equilibrium. We have attained what? Chemical equilibrium. Okay, next question here. What must we do? Is the further reaction exothermic or endothermic? Now look here what happens. Now at first, at equilibrium, our product was what? 0.4 moles per decimeter cubed. Look at graph B when they increase the temperature from 298 to 398. What is it now? We have 0.35. You can see the 0.35 is lower than 0.4. So mean that this increase hello. Yes, hello. they're saying here that is the forward reaction exothermic or endothermic? Now look at graph A. We have 0,4 at equilibrium. Are we together for the product? What about graph B? We have 0,35. So meaning to us that an increase in temperature has led to what? A decrease in the products. Okay. So because of that, it must be exothermic reaction. It must be what? Must be exothermic reaction. Must be exothermic reaction. Now they say here, explain the answer to question 6.3. What do we say? That increase in temperature, increase in temperature, increase in temperature. What has it done? Increase in temperature led decrease in the what? Decrease in the products, okay? In the product. All together. So because of the decrease in the product, then it means that in this particular case, from molecular principle, we know that an increase in temperature favors endothermic reaction. So because the forward we have gotten less products, it means that the increase in temperature is favoring what? Favors the reverse reaction, which is endothermic. So the reverse being endothermic, then the forward must be exothermic. Okay. Then they say here that how does the value of the constant Kc for relation in graph B compare to that in graph A? It is from greater than, less than, or equals to. Now, in this particular case, because we are having a lower product in graph B than in graph A, yet we know that a case is given by what? Product divided by reactants. So it's going to be lower than, because in this case, our numerator is going to be lower in graph B than in graph A. So we say it is what? It's going to be less than. So yeah, we take what? Less than. Okay. Now they said that the Kc is 0,49 at 398 Kelvin. Okay. What must we do? Calculate initial number of moles of the P2Q. Calculate initial number of moles of what? Of P2Q. Now P2Q, look at our equation. What is P2Q? Now P2Q is the reactant. Okay. All right. So we need to find out the initial moles for the reactant if our Kc is what? 0,49. Okay. And now note something here that guys, we have concentrations on the y-axis, which means that's what we have at equilibrium. Okay. So because of that at equilibrium, which is the concentration, in our table, it's better to use concentrations. Okay. Now in some questions where we have the moles, then in our table we can use moles and then later convert them to concentrations using the right table. Okay, but now in this case, because we have concentration on the y-axis, it is easier to use the concentrations. Okay, so I have my equation again here. Remember, it is what? It is P2Q plus 3Q. Okay, it is P2 what? It is P2Q gas. Okay, then plus what? Plus 3Q, which we see solid. Okay, to give us what? To give us 2PQ2. 2PQ2. 2P, which is also a gas here. So because we have concentrations, I'm going to use concentrations here. So, but I need to know the ratios in this case. So my ratios here, if I may draw the graph here, like this. Here, can draw my line just here, just for simplicity's sake. And I'm gonna have my product that side. Okay. Now you know that in our reactions, in our expression for the Kc, we don't include the solids, isn't it? So because of that, it means that in this case, my Q solid must be left out in action. So I don't have to use it. Okay. I don't have to use it. Okay, so like I said before, because I have concentrations, I better use concentrations in here. So I'm gonna, but I need the ratios, ne? So I need the ratios here. I'm gonna have, this is 1 here, all right? This is 1 here, and then here, this is 3, but I don't need, because this actually I don't need anything from this column here because to do with the gas. So here it is 2. Let's suppose we have at equilibrium. Now what I'm gonna put here now is going to be the concentration at this is gonna be supposed to be initial concentration, okay? Initial concentration, okay? Initial concentration. Then I'm gonna have the change here. Then I'm gonna have what? The one at equilibrium, okay? This might change here. I'm just putting delta here to show the change. It's gonna be now equilibrium what? Equilibrium concentration, okay? Okay, this is my, okay, this is concentration at equilibrium, okay? Now, let's check it out now. Now they said something. They said that we have 0.35 for our product. That is concentration, right? So I'm gonna put it here. 0, what? 0.35 at equilibrium. 0.35 at equilibrium. Okay. Now because initially it was 0, it was nothing. Initially it was 0 for the product, like we saw on the graph there. It means this one has been our change. So this has been produced. So here plus what? Plus 0.35. Okay. To give us the 0.35 here, which you see here, guys. Okay. Then now that have something in the row for the change. I think I better. Okay, this is my line here. This is my other line here. To avoid the confusion here. Okay. Then here I have this line for the change. This one here for the change. Okay, so I was saying that these are the equilibrium here. This is the equilibrium. But what do I see? I see that because I have some information in the row for the change, this one for the change, 0.35. So I must know what happened here. What happened here? Okay, so mean that this the more ratio is 1:2. So if I may put x here, if I may put x here, it means that I'm going to say x times 2, because more ratio is 1:2, we say 1:2. Okay, here, then put the most which we have here, which is 0.35, okay, 0.35. So if I do cross multiply, I'm going to get what? I'm going to get 2x. I get 2x equals to 0.35, 0.35 divided by 2 here. So my x equals 0.1. 0, divided by 2. What do you get, guys? 0.35 divided by 2. It gives me 0.175. So this is 0.175. 0.175. Now this is concentration, don't forget. So here, because it is what? Because it is a reactant, it must be a minus here. Okay, 0.175. Now because I'm looking for the initial moles, okay, I need to put what? I need to put something here. I didn't know anything, so I can put a variable here. Let me put x here, okay. That was the x there, but I'll convert it to moles when I'm done. So this is x minus the change, which is 0.175. So what do I have at equilibrium here? It means I'm gonna say at equilibrium, I'm left with what? I'm left with the x, okay, minus what? 0.175. Don't forget, product we add, reactant we subtract. Initially it was x. Now this is the change here. This is what we have at equilibrium. So they gave us the case C. We're going to the case expression now. We're going to the case expression. The case is 0.1, 0.49 here. Hope you can see that, guys. So we're gonna say our case C equals to what? What's our case expression gonna be? So our case C expression equals to PQ2 concentration, PQ2 concentration, that must be squared because of the 2 here, divided by P2Q concentration, okay? This is P2Q concentration. Now the case was 0, what? 0, 0,49. Now for the product here we got 0,35 at equilibrium, okay? 0,35, but must be squared, né? Okay, squared. Divided by what? Divided by x minus what? X minus 0,175. Okay, so in here, I think you see I'm gonna cross multiply. I'm going to have 0,49 multiplied by x minus 0,175. Okay, equals to 0,35 squared. Equals to what? 0,35 squared. 0,35 squared. So here, open bracket, I'm gonna get here 0,49 x, okay, minus, so 0,49 times what? Multiplied by 0,175, it gives me 0,08575, 0,08575, okay, equals 0, what? Equals to 0,35 squared, okay. Now this minus becomes a positive, so I have here 0,49x, okay, equals to 0, equals to 0,35 squared, then plus what? 0,08575. Okay, so what is my x finally gonna be? So if I check here, my x gonna be x equals to, calculator me out. What do I have on the numerator? I have 0,35 squared, okay, plus 0,08575 divided by 0,49, okay, so here it gives me 0,425. I have x as what? 0,425. Remember this is concentration, okay? So we're looking for the number of moles. Look at our question again. It says that we must calculate the initial number of moles of P2Q, which was the what? Which was the reactant, and our container was how many decimeters cubed? It was 2. You see it here, 2 decimeters cubed. Okay, so what I have right now is what? Is this initial concentration, but I want the moles. Okay, what do we know, guys? That concentration C equals to number of moles divided by the volume. So therefore, number of moles equals to what? Equals to C times V. So if I multiply here, I'm going to say 0,425 multiplied by 2, which gives me what? Which gives me, so this answer times 2, it gives me here 0,85 moles. 0,85 moles. That's my final answer here. I hope we are together. Okay. Hope we are together here. Okay, question 6.7, they say, describe the change made to the equilibrium system at t equals to 8 minutes as shown in graph B at a constant temperature. I repeat, describe the change made to the equilibrium system at t equals to 8 minutes as what? Shown diagram B at a constant temperature. So let's check it out. When t was equal to 8, check here guys, this is 8 minutes here. Now what do you observe? The product suddenly decreases. What about reactant? Suddenly also decreases. Are we together? Now these are gases. So if their concentration decreases like this, it means that in this case, because they were gases, these are gases, ne? So what must decrease the concentration of a gas? It must be a decrease in the pressure. So this was a decrease in pressure, okay? And the more so, we said that after the decrease in the pressure and decrease in the concentration here, we see that later the PQ2 it rises up, but this one the P2Q it completely goes down. So it means that now according to the general principle, we are favoring now the reaction which is forward in this case, okay? So what's our answer here? What do we tell these people? That that there was a decrease in pressure. There was what? A decrease in pressure. Decrease, a decrease in pressure. A decrease in pressure. Okay. Now they say explain using what? The principle for the criteria, how the system reacts to the change in question 6.7. Now we see that when the pressure was decreased, meaning volume increased, okay, what happened? The system favored a reaction with bigger volume. In that case is what? It's the forward reaction. Okay, if you look here we have one volume to give us two volumes, okay? So because it's one volume of P2Q giving us two volumes of PQ2, now the system, if you check here, we're getting more what? More of the product, which is PQ2, which it gets higher. So it's being what? It's being used up. So what do we say here? What are they saying again? They say here that explain by using what? Leclerc's principle, how the system reacts to the change. So the system favors what? Okay, the system favors it favors what? It favors the reaction with larger number of moles or with larger volume, okay? Which so the forward reaction is favored. The forward reaction is what? Is favored. Is favored. That's our answer there. Okay. All right. This is May-June 2024. Question 7. Question 7, May-June 2024. It says that a standard solution is prepared by dissolving 10 grams, this is the mass, 10 grams, okay, that's a mass, of sodium carbonate in 0.7 deciliter cubed of water. This is our volume here. Calculate the concentration of the solution. Now, to get the concentration depends on the available information. Once we have the mass and the volume and we can get the molar mass, then our concentration, okay, our concentration is 7.1.1. Our concentration is given by C equals to the mass divided by the molar mass, then times the volume, okay? Now, in this particular case, the mass given to us, it is 10 grams. We're going to say 10 divided by the molar mass, we're going to get it here. Now, sodium is 23, okay? But then because of the 2 multiplied by what? By 2, so 23 times 2. And then carbon is 12, okay? So plus 12 here. And then what about oxygen? Oxygen is 16 times 3, because there are 3 oxygen atoms, okay? So then times the volume. Now volume is 0.7, you can see it here. So we say here times what? Times the volume. Okay, so times the volume, which is 0, what? 0.7. So to avoid the confusion, I put a bracket here. I make the fraction all like this. Okay, so it means I have 10 divided by what? Let me get my molar mass first here. So my calculator, where are you? we said open bracket, okay, open bracket 23 times 2 and then plus 12, then plus open bracket again 16 times 3, it gives me 106. So here I have 106 for the molar mass, 106, then times the volume, which is what, 0.7. So my final answer is going to be, let's check it out, 10 on top divided by 106 times 0.7. It gives 0.135, 0.135, 0.135. This is moles per decimeter cubed. This is what? Moles per decimeter cubed. So I proceed, moles per decimeter cubed, okay? Next question here. Will the pH of the solution be greater than or less than 7? Okay. Now if you check what we are having here, we are adding we are having sodium carbonate together. Sodium carbonate. Now the sodium carbonate, what does it do? In the solution, it gives us the sodium ions and the carbonate ions. But to answer this question here, that is 7.1.2, which we want to answer here, 7.1.2, to see whether it's going to be acidic, it's going to be less than or greater than 7. Okay, let us first write the equation where they say write an equation to explain your answer. Okay, so I start with the equation so that I can see it properly. Okay, now like I told you that the sodium carbonate gives the sodium ions in solution and the carbonate ions. So if I have the carbonate ions in solution, that is CO3, the 2 minus, okay, and then I bring in the what? I bring in the water, this carbonate ions, okay, plus water, what is in a solution, what is H2O. So check this out, what's gonna happen? What's gonna happen now? If I add the water, I'm going to have something like this. I'm going to have from here I'm going to get one of the proton from here to come here and they form the hydrogen carbonate. Okay, hydrogen carbonate. Okay, hydrogen carbonate all together, then plus the OH ions all together. So the presence of these OH ions in solution, okay, they're going to make my pH greater than 7. So we say here it's going to be what? Greater than 7. Okay, so we say what's what? It's going to be greater than 7. Okay, it's going to be greater than 7. But if I want, I can get it completely. I could also have said that carbonate, okay, that is CO3, okay, 2 minus, n plus water, okay, that's plus 2 water molecules, okay. Then I'm gonna get what? I'm going to get in my solution, gonna get this H2, okay, H2CO3, then plus 2 OH ions. So any of these two can work for us. Okay. Next question here, because you see I still get 2 OH, which could makes it to be what? Bigger than 7. That's my pH. Okay. Next question here, they say that the sodium carbonate solution is titrated with dilute hydrochloric acid, that's HCl. Then the following indicators are available for this titration. So now we are titrating the carbonate solution together with the what? With the hydrochloric acid. Now they say here that we have these indicators here. Which one of the indicators P, Q, or R is most suitable for this titration? Reason for your answer by going to the data table. Now, before we get our best indicator, look at what we are titrating. Titrating this hydrochloric acid, okay, which is a stronger acid altogether. Now the sodium carbonate is a weak base. Now when you titrate a strong acid with a weak base, because the acid is stronger, the resultant solution is gonna be acidic. So because of this, I'm gonna say the answer is gonna be P. So indicator P is the right one here to be used. Indicator P. Give reason for your answer. Because we are titrating. Because we are titrating what? Because we are titrating a strong acid. A strong acid versus what? A weak base. A weak base. So that's why our equivalency point will be lower than 7. So that's why we choose that one there. Okay, next question here. They said that when 0,01 moles of dilute sulfuric acid mixed with 0,024 moles of potassium hydroxide, the total volume of the final solution is 0,2 decimeters cubed. Here, they say what's meant by a dilute acid. So, what is a dilute acid? 7.2.1. What's a dilute acid? What's a dilute acid? Now, a dilute acid is an acid, okay? It's an acid that contains less moles, or contains less acid moles in proportion to the volume of water. Okay, the volume of water. Okay. In other words, you've got too much water. That's why the acid is dilute. Okay. So that an acid that contains less acid moles in proportion to the volume of water. Next question here, 7.2.2. What must we do? They say that calculate the pH of the final solution. Now here we have our equation, which is this one here. As you can see, we have 2 potassium hydroxide plus 1 mole of sulfuric acid. Okay, give us this salt plus water. What's our mole ratio here? It is 2:1. Okay, so they give us the moles of sulfuric acid and also moles of potassium hydroxide. Let's find out, because the mole ratio is 2 potassium hydroxide versus what? 1 for sulfuric acid. Okay, let us find out the excess moles. Now our mole says 2:1, 2. Now available moles here we have 0,01 moles for the what? For the sulfuric acid. So this is 0,01 moles. So if I'm gonna find out the moles which I need for the potassium hydroxide, I can put X here. Okay, so I just cross multiply here. X times 1 gives me X equals to 2. Okay, multiplied by what? By 0,01, which gives us what? X equals to 0,02 moles. Okay, so it means that out of the 0,024 moles of potassium hydroxide, I only need how much? 0,02. Okay, so I have excess moles of potassium hydroxide, and therefore Now that excess potassium hydroxide is gonna be responsible for my upcoming pH. So I input my excess moles, okay, moles of what? Of potassium hydroxide. Okay, excess, ne? Okay, so how do I get them? By subtracting the initial moles minus the ones to be reacted. Okay, so I'm gonna say here that is available 0,024 minus reacted moles, it will be 0,02. So what's my answer for the excess moles? I'm gonna say 0,024 minus 0,02. It gives me 0,004. I have what? I have 0,04. Now once I have the moles of the excess potassium hydroxide, then I can find out the what? The concentration. Because the volume was given to us at 0,2, this one here. So my volume is what? 0,2 meters cubed. Okay. So to get our concentration, the formula says that we use C equals to N times V. Rather, C equals to N over V. C equals to N divided by V. So our N is 0, what? 0,04 divided by 0,02. So which answer do we get here? If I divide by 0,2, it gives me 0,02. I get what? I get 0,02 moles. Yes, moles per decimeter cubed. Moles per decimeter cubed. Now, this is the concentration of what? Of potassium hydroxide, which is in excess, okay? Responsible for the pH. So, now because potassium hydroxide in solution, this is what happens to it. Okay, let's check here, guys. The potassium hydroxide, when it is in solution, each potassium hydroxide gives me what? Potassium hydroxide in solution. Hydroxide gives me potassium ions, okay, plus OH ions. Now, as you can see here, the mole ratio is 1 to 1. So that now that I know the concentration of potassium hydroxide, which is 0,02, because of 1 to 1 mole ratio is also going to be the same concentration here. Also going to be what? 0,02 OH, and so in that particular case, my concentration for the OH ions, okay, is 0, what? 0,02 moles per decimeter cubed. Now my question is asking for the pH name, but let me first find the pOH. So pOH equals to negative log of what? Of OH ions. Okay, so if I say negative log, of 0,02, okay, negative log of 0,02, what does it give me? Negative log of what? 0,02. It gives me here 1,699. 1,6, okay, 1,699. Now, because I'm looking for the pH and I have the pOH, what do I know? I know pH, okay, plus pOH, it gives me 14, okay. So my pH therefore equals to 14, okay, minus what? Minus 1 comma 9. So what's our final answer here? Is 14 minus 1 comma 699, which gives us 12 comma 3. It gives me 12 comma 301. That's our pH for this resultant solution. I hope we are together. Okay, hope we are together. Is May, June 2024. The relationship between the concentration of the electrolyte and the cell potential is investigated using the following electrochemical cell by the cell notation below. So here we have aluminium solid slash aluminium ions aqueous double slash then M2 plus aqueous slash M solid. The concentration of M2 ions is changed and the corresponding EMF is measured. Okay, so they're changing concentration. So they're saying that the concentration of aluminum ions and temperature are at standard conditions. So the graph below shows the results of this investigation. Okay, so what do I have on the y-axis? It is EMF. What about here? This is the concentration of M2 ions in moles per decimeter cubed. Identify the reducing agent in this cell. Identify the reducing agent in this cell. Now listen carefully, guys, please. So whenever they give us the cell notation, please understand this side, we have what we call as the anode. Okay, we have the anode. This side we have what we call as the cathode. This is standard. Now they're saying which one is the, let's check it again. Identify what? The reducing agent. Now the reducing agent is the substituent, which is what? Which is oxidized. I repeat, the reducing agent is the one which is oxidized. Now if you check here, this aluminium solid was oxidized to aluminium 3 ions. M2 plus ions was reduced to Am solid. So the answer must be this aluminium solid because it was oxidized to aluminium 3 ions. So aluminium is our answer here. So we say that the reducing agent in this cell is what? It is aluminium. Please note that we don't say aluminium 3 ions, but we say aluminium. We say, don't put the 3 plus, we simply say aluminium. Okay, and then the next question here, they say that determine the concentration of M2 ions that will produce an EMF of 1,87 volts. Okay, now this is the concentration here, but the EMF is this side here. So we're going to look for 1,87 on the y-axis, then you come on the curve and locate what is its concentration. Okay, so now before we get the concentration, we need to know the reading on the y-axis. This is 1,70, 1,8, which means because they are 10, there are 10 small squares here. You can see this is 1,70, 1,71, 72, 75, 78, up to 1,80 here, which means each one is 1, is 0.001. Okay, so here we're looking for 1,87. 1,87 volts. So this is 1,80, 1,81, 1,85, 1,86, 1,87. Okay, so this one here, which you see here. This is 1,90, 1,89, 1,88, 1,87. This is what we're looking for. 1,87. So we go on the graph this side. Then when we go down here, you're going to find out the one we are looking for, the concentration. It must be this value here. Now to get this value here, we need to know the scale again. Now from 0,25 up to 0,50, they are also 10 small squares. Okay, so if I say 0,50 minus 0,25, I get 0,25. Now the 0.25, okay, divided by 10, it gives us what? It gives us 0.025, okay, which means each smallest square is what? 0.25. So where we have stopped, this is 1, 2, 3. So our answer is going to be 0.025 multiplied by 3, because there are three smallest squares. So what we get here, if we just check it out, it gives us 0.075. So our answer is what? 0.075. 0.075. This is moles per decimeter cubed, okay? Hope we are together. See here that how will the concentration of M2 ions be affected as the cell operates? Choose from increases, decreases, or remains the answer. Now let us check M2 ions in our cell notation. Now in our cell notation, like I told you, this side is for the cathode. So because the M2 ions appear at the cathode, where reduction takes place, it means the M2 ions are going to be reduced to give us M by this equation. So the M2 ions will be what? Reduced by what? By 12 to give us what? To give us the M. So because of this reduction, the M2 ions, they're going to decrease. So we say decreases. We say what? We say decreases. So the answer here is what? Decreases. We say decreases, okay? Okay, then we say now explain your answer if you did not guess, because the M2 ions, okay, they are at the cathode, okay, cathode where reduction takes place, at the cathode where reduction takes place, where reduction takes place. So they're going to be reduced. Okay, next question. Potassium nitrate is used in the salt bridge of this cell. To which electrode will the potassium ions move in the salt bridge? Choose from aluminium or M. Okay. Now the potassium ions, they are positive ions. Now where they should go must be a deficiency, excess of negative ions. I repeat, the potassium ions are positive ions. So the cell where they should go should be having deficiency of what? Or should have excess of negative ions. I repeat here now, this one, because of oxidation, you're going to have excess of the positive ions. Excess of what? Of the positive ions. Now here where reduction takes place, um you're going to have you're going to have what? Deficiency of what? You're going to have deficiency because you're going to have excess of the positive ions, negative ions here. So because of that excess, because of excess of the negative ions, okay, it means the potassium ions must come towards M. So it must be towards M. Because in that M cell we have excess of what? Excess of the negative ions, and so for that matter, the potassium ions must come and do what? And neutralize them, okay? So we're gonna say it is towards M. It is towards M. It is towards M. Okay. We say it is what? It is towards M. Next question here. They said that now 8.5. Identify metal M with the aid of a calculation. Now to get our metal M, we are going to find out its E standard for the cell. Okay. And then we see what happens. Identify metal M. what do we know to identify metal M? We're going to the formula, okay? But before we do so, let's check the graph again. Now you know what metal M to be identified, because this other part of the cell was at standard conditions, this one which is aluminium, so M must also be at what? At standard conditions, where we have which concentration? Where we have 1 mole per decimeter cubed. So it means we must locate its corresponding EMF. So if I may use the red color here, the red color like this, okay. Now it means that in this particular case, my EMF from that is for this cell when the M is in operation should be corresponding to this one here, which is this is the concentration. So I must move up, okay. I must move up and find out which corresponding EMF it is. So this is where I am right now. I'm here. Then I must go to this other side to locate the corresponding EMF. As you can see, it is 2. Okay. So now using the equation, I'm going to find out which element is M, because I know that the E standard for the cell, okay, is my cell here, okay. I know that E standard for the cell is blue color now. I know that E standard for the cell equals to E standard, okay, for the cathode, okay, then minus what? Minus E standard for the anode, okay. So now this is 2,0, 2,000 here. Now the one for the cathode, like we said, this side is anode side for cathode, so I'm going to put E standard for M, because I'm looking for I want to identify M, okay. Then the one for the anode, we saw it is aluminium, so I'm going to check for aluminium from my table 4B. Now the corresponding E for aluminium, my table, where are you now? My table, where are you? So the E theta for aluminium from here, as you can see, it is what? Negative 1,66. So I'm going to say here minus negative 1,6 and 6. So it means I'm going to have now 2, then becomes positive, 2 minus 1,6 equals to E standard, okay, for M, okay. So what do you get, guys, when subtracting? Here it gives me 0,34. I get what? 0,34 volts equals to my E standard for M. So I check here in my table where I have 0,34, and then that will be the metal M, 0,34. If you check here, 0,34 is this one here, 0,34 is this one here, and then so it must be copper. So my metal M is what? It is copper, which is U, which is copper. All right, let's proceed here. What else do we need? What else do they want now? They say that metal M is now replaced with magnesium, that's Mg. Which electrode, aluminum or magnesium, would be the anode? So now this cell contains aluminum and magnesium, okay? So which of the two is going to be the anode? So we go back to our cell, our reduction potentials 4B, to compare aluminum and magnesium, okay? Now if you look at aluminum and magnesium, let's check it here. Aluminum, where are you? Aluminum and magnesium. So here we have magnesium just on top here. So this is magnesium here, okay. Now the magnesium, this one here, which is on top. This one is aluminum, which is just below here. So now the one which is more reducing, it forms the anode. So magnesium will form the what? Will form our anode. So the anode will be what? It will be magnesium. Okay. So 8.6.1. Our answer is what? It is magnesium. It is magnesium. So magnesium is going to be our what? It's going to be the anode. Then they say refer to the refer to the relative strength of the oxidizing agent to explain your answer. Now check this out. They say refer to the what? To the strength of oxidizing agents. So here, now when I want to answer this one here, I must look at the side of oxidizing agents. Ne? Let's check it out now. Oxidizing agents. Compare magnesium and aluminium. Now this side we have increasing strength of oxidizing agents. So if you check what we have here, magnesium 2 ions are more oxidizing. Check it out, our arrow is going down. Sorry, I beg your pardon. The aluminium 3 ions are more oxidizing than magnesium 2 ions. That's our reason here. We say because aluminium 3 ions are more oxidizing than what? Than the magnesium 2 ions. Okay. So we say because aluminium 3 ions are more oxidizing than what? Than magnesium 2 ions. What did I say? I said because the aluminium 3 ions, okay, aluminium 3 ions are more oxidizing than what? Than magnesium 2 ions. And so because of that, so magnesium will be oxidized. Magnesium will be what? Will be oxidized. Will be oxidized, okay? Okay, question 9. Yes, question 9, May, June 2024. The simplified diagram below represents the cell used for electroplating ornaments with the silver. P and the Q are the two terminals of the battery, okay? These are ornament here, this is silver electrolyte here. State energy conversion that takes place in this cell. Now, because we are using electricity to get the chemicals to put on the seal on the ornament, it's going to be from electrical energy to chemical energy. So you're converting from what? You're converting from electrical energy to chemical energy chemical energy. Okay, then next they say which terminal of the battery P or Q is negative. Now note that whatever we want to electroplate, we must put it on the cathode where reduction takes place. So that cathode is the negative. So in this particular case, negative is this P. Okay, it is P. They say here, write down the equation for the half reaction that takes place at the cathode. Now this cathode here, what's happening there is a reduction, like I told you. Now because these are silver ions, we must reduce them to give us silver, which we quote as a layer on this ornament. So you're going to say that the silver ions, okay, silver ions, they're going to be reduced by the electrons, okay, to give us the silver solid, which you're going to be what? You're going to hold on this ornament. That's the equation here. Now here they said that calculate the current needed to electroplate the ornament with 3,25 grams of silver. of silver in 30 minutes. Okay, so now because they gave us the grams of silver, let's get the moles of silver. Okay, how do you find moles of silver? How do you find moles of silver? Now the moles of silver, because we have the mass, the number of moles of silver will be given by what? How do you find number of moles of silver? We divide the mass by the molar mass, ne? Mass over molar mass. Now they gave us from here we see it is 3,25. Okay, this is 3,25. Now the molar mass of silver, if you look at the periodic table somewhere here, we can see that it is this 108 here. Okay, 108. That's our molar mass for silver. So we come here, put it here. We say this is divided by 108. Okay, 108. Now if you divide by 108, how many moles do we get? 108, we get 0, 0,03 moles. 0,03 moles. So the number of moles of silver is how much? It is 0,03 moles. What does the question want us to calculate again? Check it again. They say here that calculate the current. We're looking for the current needed, but how do you know how to get current? Now current, we know that current is the rate of flow of charge. So if you can get the charge and divide by change in time, we can be able to get our current. So our task is to find the charge here. Now that we know the moles of silver which has been used, must be the same number of moles of electrons because mole ratio is 1 to 1 from here. Okay, so we are going to say that the number of moles of silver, okay, or the number of moles of electrons is the same as that of silver. So the number of moles of electrons is the same as the number of moles of silver, which is what? Which is 0,03. Why? Because of 1 to 1 mole ratio. Hope we are together. Are together? Now that I know the number of moles of electrons, then I can be in position to know the number of electrons. Why? Because I know from the formula says that the number, okay, and the formula says that the number of moles of electrons, okay, given by the number of electrons are together, then divide by Avogadro's number, which is Na. This is number of what? Electrons. These are moles of electrons. So from here, to get my number of electrons, which I'm going to call capital N, okay, equals the number of moles of electrons multiplied by what? By Avogadro's constant. So here I got 0, what? 0,03. 0,03. What about Avogadro's constant? We know it is what? It is 6,02. 6,02 multiplied by what? By 10 to the power 23. So calculators, what do you get there? My calculator here, it gives me 1,806 equal to 22. 1,806, 1,806 times 10 the power what? The power 20, the power 22 electrons. Now these are the number of electrons. Remember, I'm looking for the charges, ne? These are the number of what? Electrons, ne? Now another formula which we know to get the number of what? The number of electrons. What do we normally do? We know the number of electrons. Now this capital N, talking about number of electrons, okay, is equal to the charge, okay, to the charge divided by electronic what? Electronic charge. So that my charge, which I'm looking for, given by the number of electrons, okay, multiplied by what? By electronic charge. Okay, so here we got what? 1,806, okay, times 10 to the power 22. What about electronic charge? We know it is 1,6, right? Exponent what? Exponent 19. So this is 1,6, 1,6, okay, times 10 the power negative 19. So what do you get calculators there? Anybody with a calculator? Here it gives me 2889 comma 6. 2889, this is 2889 comma 6. So I know the charge, so I can come back here to get my current, okay? Because current equals to charge divided by what? Divided by the time. So I'm gonna say 2889 comma 6. They gave us 30 minutes, but it must be in seconds. So we say 30 times what? Times 60. Okay. So our final answer here, we are getting calculators. We get here 1,61 amperes. So the current will be 1,61 amperes. All right. Thank you so much for watching. Catch you again in our next video. This is Patrick Kamala, tutor, educator, psychology Pulukwani. You can reach me on 0785 222 041. Bye bye.